It's on? Yeah. Okay. Good morning, one and all. So today we are going to do one of the practicals under the course head CL501. That's the fifth semester practical. What we are going to do today? This particular lab 501 is essentially streamlined at aiming all the practicals which we will be doing under this head are the application oriented practicals, right? Now the first in line will be the estimation of iron content. In various food items. This is what we are going to do, right? Now, why we are saying like estimating iron content? It's quite important that we know the nutrition value of our food, and this is where the practical aspect of this 501 comes into picture. We are going to use a colorimetric method. Right? Colorimetric method by estimating the concentration of iron as a complex, a thiocyanate complex, as a function of concentration. We will be making a calibration plot, and then we will be estimating the different iron content in various food items what we have got. Now joining in today, we have two of our friends. It's Sonali, yeah, that's here, and yeah, hello. And henchman Rupesh. Can you show it yourself, Rupesh? Turn it around. Yeah, see, without him things won't be possible, right? He's the reason why we are talking to you, right? So what we are going to do, a very simple approach, right? A very simple approach. We are going to extract all the iron content from the various food items. We'll see what Sonali has in store for us today. And then we are going to extract all the iron from it by making a ferric chloride solution, right? You're treating it with HCl, concentrated HCl, and then filtering it out, centrifuging it. We'll talk about all of these steps as we follow. And then we will be treating it with thiocyanate. Now these are the colorimetric methods what we had done in the lower semester. So we are going to bank upon whatever we have learned to put it into a practical aspect over here. Alright, so let's get started what all things we have in store, right? And we will talk more about the practical as and when we move on. Which can you please come here? Right, the different food items what Sonali has for us today. Wow, that's the sprouts. Can you see how healthy it looks? But let's see, are they good in iron or not? That's our soya bean, right? Yeah, lovely banana. Yeah, a morning breakfast item, a potato, beetroot, very nice. That's we have a jaggery and our lovely seasonal mango. Very nice, right? So what we had done already for you, so we had weighed 50 grams of each of these food items. We had processed it. Now processing means what? You burn it, you caramelize it, you make it into ashes, and then you treat it with acid. Now how do we do it? So can you show it for the jaggery? Do you have the jaggery ready for us? Yes. Yeah, she has the jaggery ready for us. Can you please turn it on? Yeah, see. You have a very nice jaggery over here. Right, can you see? A very little. What we had used is 50 grams of every food item, and believe me, it takes time to do all of those 50 grams of things, right? Now for demonstration purpose, we are showing you a very little amount. Can you show it? Yeah, Rupesh, just zoom in. There you go. Yeah, it started to melt already. See, that's the reason why we chose jaggery. It goes very quickly. Can you see the change in the physical form? Oh, nice fumes coming. Oh. Bit slow. Yeah, see, we are burning the jaggery, caramelizing it. right? Fuming. Thankfully the exhaust is working. All the fumes are going that way. In normal scenario we do it in the fume mode, but right now just to show you a little tiny bit, we are showing it here on the bench. But whenever you are going to do it, do this practical, you are going to do it. You can stop it. We don't need any further. So they got the idea, like how you have to burn it, turn it into ashes. So all the ashes and all, you digest into hydrochloric acid and then filter it. So these are the kind of solutions what you will get. This is for the beetroot. Yeah, all the iron content, if at all it is. Right. This is what the solution for the soya bean. Wow. I hope there is a lot of iron here. This is what? A potato. Right. And then you see those sprouts. Right. And this is what? Is the banana solution. Right. Now, I'm not sure if and let's move on. That's the mango, and then finally that's the jaggery. Right. Now what I really want you to focus upon, can you just see? There are a little bit of particulates you will see here. So what we had also done, these solutions were centrifuged at 10,000 RPM for 10 minutes, and we are using only the supernatant to process it further. Right. Now before we estimate what is the iron content, that's the processing of the food items. You take the supernatant of the centrifuge items and then you keep it ready. Now before we know, like can we move to the board again? We need to make a calibration plan. Right? This is what you might have done in the lower semesters, the calibration plan. So for that what we had done? We had used iron chloride and then we get sodium thiocyanate to get the iron thiocyanate complex, which is red in color, right? So everybody knows it. So essentially, this is what we get, right? If this is my wavelength plotted on x-axis and this is the absorption, right? This is the typical absorption spectra what one would see, and this is the place what you call it as the lambda max. Oh, x, right? Now for this lambda max, for this iron thiocyanate complex, the lambda max happens to be 595, right? 595 nanometers. Oh, my apologies, 495 nanometers. Now, the question I am going to ask, and we will come back to this graph in a minute. Let's move on to our spectrometer. We are moving back and forth. This is how I really love doing things. Right? Look at the filter over here. Yeah, can you zoom in on the panel, Rupesh? We have 405, 430, 465 filters. So these are the selective filters, colorimeter or a spectrophotometer. 506, right? After 465, we have a direct jump of 506. Where is our 495? We don't have it. So does that really mean that's the end of our experiment? Right? I don't think so. Let's go back to our graph again, one more time. If lambda happens to be 495 and we have 505 nanometers, right? What you had just seen. Right? And on the left side it was 465 nanometers. We do have some absorption over here. It's not that everything is lost. We do have significant, not some absorption, in fact, significant absorption. So if at all you don't have the possibility of the exact wavelength, better you start working at the nearest wavelength what you have got in your spectrometer. Fine. Now let me do another plot for you. Now suppose this is the kind of, that's not very good color choice, isn't it? Maybe I'll use red. Yeah, it's visible. Rupesh, does it look red on your camera? Yeah? It looks red, right? Now the line which I am drawing here is the absorption as a function of concentration. So we actually have a 2D curve over here. So here we are plotting concentration of the sample, wavelength. You fix the wavelength at a fixed wavelength. Let's say this is what is at 495 nanometer. You fix your spectrometer to 495. If at all you have it, then you get this kind of stuff. Lower the concentration, lower the absorbance. Higher the concentration, higher is the absorbance. Just following Lambert-Beer's law, the linear curve. What happens if you don't have 495? Right? As I said, not everything is lost. We will use this purple color. Let's see if that's visible. You will get something like this. This is what we have got in our spectrometer, 505 nanometers, right? So you do get two parallel lines, the same trend, and this is what exactly we are doing. We are doing the relative estimation of the food items, and we are doing the calibration plot at the same place, so it should be okay, right? It should be okay, right? Now if you have this is what your absorbance is, what? Epsilon CL. We do have mostly in the literature the value at the lambda max for a particular experiment, the standardized experiment. We call it as lambda 0, let's say 495 nanometers. But then for 505 you have to estimate the value of this epsilon so that you are able to measure the concentration as a function of absorbance, given that the L, the cuvette path length, remains the same. You cannot alter it for the given equipment, right? You cannot alter it. So we are good. So in our colorimeter we have 505. We can carry on with it, right? We can carry on with it. So let's see what we get, right? We have already made some standard solutions, the calibration solutions. Can we have a white paper so that we can show you the gradation? So we already are making. Rupesh, can you please come closer? So Sonali is running around to get the white paper to show you as a background. Yeah, she got one. There you go. Thanks, Sonali. And these is what I'm going to put it down, different samples as a function of concentration. This is like 0.01 millimolar, 0.02 millimolar, right? Oh, close it, 0.03 millimolar, right? Can I have the next one? Yeah, 0.04 millimolar, right? 0.05 millimolar, 0.06, 0.7, that's a 0.8, that's 0.9, 0.10, 11, right? 0.11, 0.12, and we ran out of the white paper. Doesn't matter, we'll improvise. We'll put it down here. 1.3, 1.4, and 1.5. Now remember the kind of straight line which I had showed you. Look at the gradation, the lowest concentration going towards the highest concentration. So just by looking at it, you can say like very likely we might be having a good calibration plotted. Can you just scan it from left to right? Let everybody see the gradation of the color intensity. Yes, yes. Definitely we'll be sharing all the these things, values, the absorbance values with you. Let's move them aside for now so that we have more space to work upon. And moving here. Okay. Can you just put them on the rack please for me? And to prove our point, we are also going to do measurement onto this sophisticated machine. Very small but very handy. Let's fire it up. What happened? Oh, there it comes to life. So it's a nanospectrometer, right? So let it just come to life on its own. Right. Now we are wanting to, okay, so it says initialization passed, right? And then, why don't Sonali, you take over? You
go to more apps.
Yeah, more
And
apps.
choose wavelength.
Because we are wanting to measure only at a single wavelength, right? Rupesh, can you just come in? I'll just talk from here so that everybody can see. Yes. Can you select the wavelength, Sonali? There she goes. She selects the wavelength. Right, by default. There she selects the wavelength. There it entered. So you have the flexibility of selecting a wavelength. It's a continuous wavelength system. So you can select practically any wavelength over here. Right? Unlike the selective filter stuff. Now what we are going to show you here, the values. Right? The values we will be measuring at the selective filter spectrometer, colorimeter, the less sophisticated machine, and this seems to be a more sophisticated version of a spectrophotometer. And then let's see if our results match up. Now what I am going to do now, I am going to show you how did we process the sample. Now remember, this filtrate, what we have got after digesting the food ash with the concentrated HCl, we had filtered it and centrifuged it. Now the filtrate looks so clear, right? So clear, right? Now we are going to add some hydrogen, right? Let me put some chalk here. This is my 1 ml pipette. Let's set it up for 1 ml. Let's have some thiocyanate in the beaker, right? Now our pipetting scheme says I should be adding this thiocyanate to my, I'm calling this as the test solution, right? So that you really should be convinced that there is a change of coloration here. Now the minute I add thiocyanate, can you see something is happening? Yeah? See, can you show them something is happening? It was, that 1 ml I had added already. Let me add the second ml. Let me add third. Fourth. And there goes the 5. Right. Let me discard it. Let's put it back here on the stand. And right. Can you see the change in color? The solution was so clear before. Now it has become quite red. Yeah. We had purposefully used with a higher concentration side so that you can really see the change in color. Now what Sonali is going to do now? She is going to fire up the other machine. Yes. And she has got multiple cuvettes. Right. Now what are you planning to do? Which cuvette you will be using? You have 3 here. Should she be having 3 cuvettes here? No. So she should be using only 1 cuvette for the blank, and the same cuvette she should be using for measuring this sample. Right? So we have to negate all the other factors. We just want to be sure of that the change in color, the absorption is by the virtue of the solution and not any other factor. Although look at all those cuvettes, right? What Sonali is using, and look at this one. They all look the same, but believe me, there are some manufacturing differences, tiny little bit. They will affect your readings a little bit here and there. So why take a chance? It's a good practice. So she had done an auto 0 just now. So see, the wavelength is set at
505.
505. Is it 505? Because I cannot see it from here.
Yes.
Yeah, it's at 505. Yeah, I can see it through the camera. It's 505. What she has done, she has added a blank to the cuvette and did auto 0. There she go. Then the absorbance is at the 0 baseline. Now let me give this sample to her and let's see what measurement we get. You can throw the blank here in the discard. Yeah, can you get rid of the residual blank solution? So we don't want any dilution happening to our sample because of the blank. So these little bit precautions really go a long way. Doesn't matter which kind of practical you do. There it is. There it is. There it goes. Can you zoom in onto the panel, Rupesh, a little bit? Yeah, it's better. 0.72. Can you see this absorbance value? 0.72. Right. So let's make a mental note of it. Now, can we have the same sample getting measured over here? We will be running the blank first. Yes, please zoom in. Right. We'll be running the blank. See here. Yeah. So now you go ahead. Change the cuvettes. Can zoom in here. So there is a cuvette holder opens up. That's beautiful. And right now, just a minute. See, you have to make a mental makeup first. Which way you are going to put it? See, 2 sides of this cuvette are graduated, so they are out of question, so they cannot come in here. So with a marker, where is the marker here? You make a small mark on the cuvette. Like for me, this mark is always going to be towards me. It cannot happen that you put a blank this way and put the sample that way. It shouldn't happen. If you put this mark over here, the blank is always facing towards me. This is how we are going to work. Can you put it back again over here? There it goes. Yeah, can you see the baseline? Right? It's a bit shiny. Maybe Rupesh, can you turn off this light so that this shining of the screen is gone? Much better, much better. Can you see this red baseline? It's quite flat, right? Now we can take out our cuvette, give it to Sonali again. There she is, getting rid of every residue of the blank from the cuvette so that our sample doesn't get diluted. Then we can use rest of the sample in this cuvette, the maximum capacity being 1.5 ml. Right, nice color of the solution. Gentle cleaning, right? Cleaning wise, again a caution. We always prefer, can I have the tissue? Clean it in one direction, right? Gently clean it in one direction. You don't rub it up and back and forth, because then you will have the residual cellulose traces, right? And see this mark again coming towards me. Yes, there it goes in the machine. And she says test, give a test name, right? What do we get here? 0.91, right? 0.91. And what was the value here? Back again? 0.72. Can you remember? Was it 0.72 or 0.78? Sonal?
0.72.
0.72. Yeah? Now let's go back to our graph again. Right? The sample, what we measured in the sophisticated machine at 495, we had the value of absorbance as 0.9. How much it was? 1. And here at 505, I have got 0.72. Right? Now, if this was to be correct, can we set up our sophisticated machine, the nano spectrophotometer, at 505 and see if we get the same value? Can you do that, Sonali? Set the wavelength at 505 and look at the measurement. So what we have done so far is doing at randomness. Right? Yes, you put the sample back in the tube. Yeah. Same solution, but then you have to first set the wavelength to, can you come in here, Rupesh? We are setting the wavelength to 505 so that everybody can see, right? So you have here, and now we are going to set it to 505. Write exactly what our colorimeter is, right? We do the blank again at 505. The wavelength has changed, right? We have to do the blank again. Wipe it through. Okay. Run the blank for me, please. Wow, this time the orange line, still the flat one, that's good. Then take it off again. Get rid of all the blank solution. Tap, tap, tap. There it goes. Yeah. And back the same solution into the cuvette. Can you recall the value what we had written? 0.72. Right. Let's see the moment of truth. Are we going to get in the same closer value, and let's say sample. It is 0.847, not very off, not pretty much off. So we got 0.84. Right, let me write it different color here. Which was 0.72, we got 0.84. Right? Similar range, if not exact. It's not that it is 1.84. No, it is 0.84. We are in the similar range. Now the very fact is we have measured, right, the calibration samples and our food samples on the same instrument. So we had measured the calibration samples on both the instrument at 495 and 505. Now we are going to write down the values, right? Let me rub it off. Right, can you have that notebook, Sonali, where you already have the sample there? So, first we will be writing the calibration plot, right? So, 0.001 molar, right? We had started. We had optimized kind of these concentrations before making this video so that we get a linear plot for wavelength against absorption, because that's where the Lambert-Beer's law holds. If you go too high, again you get tailing off effect. If you go too low, again a tailing off effect. So you have to optimize the region where you get the linear plot. And the selective filter machine, typically the confidence limit range is between 0.1 and 1.0. If anything goes below this or anything go above this in this machine, I would be, a bit wary about. Should I consider or should I not? Next is 0.02. Yeah. So what is this? This is concentration, and this is like absorbance at wavelength 505. So these are all selective filters. And what we had done at the lambda max using our spectrophotometer, we had also measured the absorbance at lambda 495. 95, right? So then we have the concentration 0.03, then we have 0.04, yeah, 0.05, 0.06. Yeah, it will be quite long time, so let's make it 0.07, there it goes, 0.08. So now just stop me when all the concentrations are done, okay? Yes. 0.09, yeah, 0, not 6, huh? And 1 point? 0.10, yes. See? These silly mistakes happen. Typo on the board. Huh? 0.11, correct? Yes. We are going in an increment of 0.01. Can you notice that already? So the next should be 0.12. Good. Is the board going to be enough? It should be enough. I have to make sure it's enough. 0.13. Are you getting all the values, Rupesh? 0.14. Oh my God. And the last. Just enough. Else I have to request our institute to give us a longer board. Thankfully, we managed. Right. So, can you tell me the absorbance value for this one? 505. We have this
0.07.
0.07. Right. Let me make it slightly better. Yeah. A feel good factor should come in. Yeah. There you go. Yeah.
0.085.
0.085. That's what she says. Okay.
0.15.
0.15. Right. I'm going to ask one question after I've written on all the values. 0.174.
174.
All right. 0.21.
21. 255.
255.
0.26.
26.
329. 0.35.
5. Yeah.
0.433.
Right.
0.41, 0.518, 0.48,
Not 6, huh? Or 8.
0.604,
Right.
0.585,
5,
55,
5, 5,
yes, 55,
50,
0.690,
6, 9, 0. Does it look like 9?
yes,
Yeah. Okay. 0.63,
0.63, 0.791,
right. What is next?
0.69,
6, 9,
0.869,
0.869. Right.
0.75,
0.75,
0.950,
0. Hmm.
0.81,
81,
1.041,
right.
0.89,
Hmm.
1.139,
Right.
0.95,
Hmm.
1.223,
1.223.
1.04,
Oh, already 1. 1.04, just above 1. So we are still in the confidence range.
1.318,
1.318. By the way, this I will be more confident between 0.1 and 2. So it's okay. I can trust these values. Now these are only 2 figures after decimal. These are 3 figures after decimal. What should I do? Should I just round it up? That will be more sensible thing to do. Right? The round off figure. One can do it like 0.085, so you can look at 0.09, 0.17, 0.26, 0.33, 0.43, 0.52, 0.60, 0.70, 0.8, 0.87, 0.95, right? Then 1.04, right? 1.14, 1.22 and 1.32. We just round it off, right? And then we have the comparable values written over here. Now, can you see it's quite a linear trend, right? Pretty much what we are wanting to show you here. Doesn't matter which wavelength you have used. This is that point we are trying to prove over here. Doesn't matter, right? Now, what Sonali already has done, she has already got some absorbance values for the food items, right? And she has measured it onto this selective filter system only, not on this one. Now, I'm sure by this time you are convinced that it doesn't matter whether you measure it in a selective filter spectrometer or the nanodrop, the sophisticated machine what we have got. Can we just write it down? Let me make some space for those ones, so I don't want to rub off my calibration plot. And it has, all the food items has been measured at the wavelength 505. Okay, right, Sonali? Yes. Yeah, she says yes. She says yes. Oh, that was right, okay. She takes a different color to avoid confusion. So lambda 505. Food items. Right. Can we have those values, Sonali?
yes,
What are all the values? Lovely. Fantastic. What's the first food item?
soybean,
Soybean. So we write soybean, yes. What the absorbance value should I say? This is
0.
the absorbance what we are saying, right? absorbance value we are saying for the different food items, right? Absorbance at lambda pi 0 pi. That's the selective filter instrument what you had used, right? So, what is it?
0.82.
0.82. Next one,
Mango.
mango. Yes,
0.39.
0.39. Oh, some iron is there.
Beetroot.
Okay. Beetroot. Quite red in color, isn't it? Yes.
0.13.
0.13. Ooh. No iron. Okay.
Sprouts.
Sprouts. Yes.
0.98.
0.98. Wow. Wonderful.
Banana.
Banana. Yes.
0.15.
0.15. Oh, almost next to beetroot. Okay.
Spinach.
Spinach. What's the
No,
spinach
sir.
there?
No, sir. Potato.
Potato. Yeah, that's what I was wondering. There was no spinach in the food you had given me, right? Let me see. There were 7, right?
Yes.
Potato. Yes.
0.15.
0.15. And
Jaggery.
jaggery.
0.93.
0.93. Lovely. My granny always used to say, eat jaggery if you are anemic. She was right, isn't it? Because just have a look at it. 0.93. Wow. Quite high. Quite high. Right. One can plot the calibration plot, get a linear equation, and then feed in this absorbance value and get the corresponding concentration. Fantastic. Just fantastic. Right? So now you know, out of the different food items which we had chosen for today's experiment, which gives you the maximum iron content, sprouts and jaggery. That's the conclusion you can draw given the values in the board. Right? So that brings us to an end to this practical. I'm sure you had understood the very concept what we were trying to convey. And signing off from Center for Excellence in Basic Sciences with my friends, that's Avinash Kale. Bye.